Just wait for a couple more minutes, then we will start. About the paper, I don't have much idea because I have not done this course or given the exam in that particular course. But mostly it is MCQ based questions. So mostly you will find MCQ or MSQ based questions. Very less MSQ I would say, but MCQs are. Um, I think most of the times MCQs are maximum. Okay, let me start. Today is the last problem solving session, the week 12 of the introduction to atmospheric and space science. And first I will discuss about the assignment questions, whatever the theoretical and fact based questions which are there in the assignment 12. And after that, the numerical questions I will try to solve. Three numericals were there in that particular assignment. So I will solve those three questions. And after that, what we will do is that there are some previous year assignment questions which I have not solved so far. Maybe some may be repeating, maybe I have solved. But some questions which I have not solved, that I have kept here, so that if those questions also come, then you can solve those questions. You can see some MCQ based questions are there, and what I will do is that in finding out the solution of these MCQ based questions, we can revise certain concept based on these particular questions, which will be helpful as a revision kind of thing. And for the exam, I would say that the PPTs which are there in the NPTEL, go through that very well, so that, because most of the questions generally in other subject, I know about other courses which I have given exam in NPTEL. So in those courses generally the PPTs, if you read it carefully, you will get most of the questions, and others are numerical questions. We have solved so many numericals in the problem solving session, so that will be enough, I think. And of course the assignment questions you should look, which we have solved also in the problem solving session. So all these questions are there, and ultimately at the last, if we get time, then we can write the key formulas corresponding to the concept of the Debye potential, because most of the numericals were there, then particle nature of plasma, and we will end up there. So let's start from the beginning, where we will solve about the assignment questions. Let me go to the assignment. So this is the assignment 12 corresponding to the week 12. If you see the first two questions, these are numerical based questions. I have already put into the presentation, so we will solve that. Let's go straight away to the third question first, because it is a kind of a fact based. So the question says, which of the following is responsible for the ring current that produced in the ionosphere of the Earth? This ring current is nothing but the planetary ring current. They are saying about the planetary ring currents. And which of the following is responsible? So the options were there, like photoionization, then longitudinal drift of the charged particle by geomagnetic field, then vertical drift of the charged particle by geomagnetic field, and neutral wind. So we have not seen the concept of the neutral wind, so it is already getting eliminated. Photoionization is the process through which ions are produced. It's not for the ring current. Only the ions are produced using photoionization. But if you see these two options, like longitudinal drift of the charged particle by geomagnetic field or vertical drift by the charged particle, it can be a possibility from these two options. But if you remember, in the planetary ring current, the way it is there is that you have, so this is the third question which I am discussing. Now you have, this is your Earth, suppose, and this is your radius. Let's consider it RC, corresponding to the centrifugal force. So your FC is actually in this direction, and this is the Earth, and this is suppose the north-south pole. You have the magnetic field like this. So you have this magnetic field in this direction, okay, and the gradient of magnetic field is also in this direction. So these are nothing but the radial direction or k cap direction. This B is in the j cap direction. Of course, it is minus to plus. You can assume anything right now, because we just need a direction. Okay, so B is in this direction, grad B, and RC is in the vertical direction, that is the k cap direction or radially outward direction. Now if this is the case, now if you write only the velocity, if you write, even if you don't write the planetary ring current expression, or even if you write that, so if you remember, this is the J gradient. I am not writing the entire expression, I am just writing that it is proportional to B cross gradient of B. In fact, you can see that the velocity also has this particular expression. Again, J, the current density in that centrifugal thing or curvature drift current density, is proportional to RC cross not grad B but B. Therefore, this current density, or what you call as the current, this must be perpendicular to B, must be perpendicular to grad B, because this is the cross product. If G, that gradient, is proportional to B cross grad B, that means J grad, or this gradient drift, is perpendicular to both B as well as gradient of B. Similarly, JR is perpendicular to both RC as well as B, because it is in the cross product. Therefore, this current is perpendicular to B, perpendicular to grad B, as well as perpendicular to RC. That means it is perpendicularly J or K cap direction, because we see that B is in the J cap direction. It does not matter whether it is in plus J or minus J. FC as well as gradient of B, or RC or gradient of B, is in the K cap direction. Therefore, the only possibility that the perpendicular direction which is left behind is the I cap. And in atmospheric science or space science, we generally denote this I cap as the longitudinal direction. Okay. So this, in this longitudinal direction, there will be a drift, and because of that, the current will be produced. Okay. Now, why these B, grad B and RC all we are considering? Because the J total is actually nothing but addition of J, the gradient, what you call as the planetary current density, plus JR. Therefore, longitudinal direction drift is responsible, or this is the answer of this question. So, if you look into it properly, which of the following is responsible for the ring current that produced in the ionosphere of the Earth? It should be the longitudinal drift of the charged particles by geomagnetic field. Simple. Okay, not the vertical drift. Fine. Now, the fourth question is, the invariance of the dash is the basis of one of the primary schemes for plasma confinement called the magnetic mirror. As you know, the magnetic mirror concept, it's known to us that it is magnetic moment which is remaining constant. In fact, another term which remains constant, which is the kinetic energy, and if you start with that, you will get the magnetic moment as constant. So if you see the concept of the magnetic mirroring in the NPTEL PPT also, you can see, or in the problem solving session in the previous session I have discussed also about this concept of the magnetic mirroring. You can see that also, or the videos of the NPTEL also you can see. So there you have this W parallel plus W perpendicular, means the total kinetic energy is 0. This is the energy conservation. From there, from the previously done thing, we know that this half mv perpendicular square is actually mu into B, where mu is this magnetic moment. So this is the magnetic moment. Okay. And this will be nothing but W perpendicular. Why? Because V perpendicular square I have written. Okay. Now, if you go further, d dt of half m V parallel square plus V, this W perpendicular I am writing as mu B, that is equal to 0. Now, this half mv parallel square, or we have actually got dw parallel by dt is actually minus mu dB by dt. You can write dBz, because the way we have derived here there was this. So just put the expression here, so it becomes minus mu dB dt. I am writing B, not bz, plus d dt of mu b. So what it will be? One time it is mu dB dt, another time it will be b du mu dt. This is equal to 0. So now you can chop out these things. So what you will left behind is d mu dt is equal to 0. What does this refer? That magnetic moment is constant. This is what they are telling as the magnetic moment invariance. It's not varying Why? Because it is constant. So this is the concept for the magnetic mirroring. Confinement of charges, trapping or reflection of charges or plasma particles is the concept of magnetic mirroring. Okay, so if you follow it, the magnetic mirroring concept from the PPT or the problem solving session, then you will get this. We have derived mu is equal to constant. So I am starting from a energy conservation, and based on the W parallel and W perpendicular expression, we can get this mu is equal to constant. So it is the invariance of the magnetic moment which is responsible for this magnetic mirroring concept. So the accepted answer is magnetic moment. Again, there is a numerical. I will talk about that. Okay. This is a straightforward question, as we are discussing that which of the following is used for the confinement. See, this confinement means trapping. So if you remember this confinement, let me write, this is the sixth question. So confinement is nothing but trapping of plasma particles. And this we have seen in the magnetic mirroring concept. Okay, this is related to magnetic mirroring, where you have a condition that if theta is about what you call as if this theta is greater than equal to sine, or I would say that this is not the constant, this is the sine square theta. If it is greater than equal to B naught by Bm, where B naught is the original magnetic field and Bm is the maximum magnetic field, then this is trapped or confined. So this is the concept which we have got in the magnetic mirroring. So confinement of plasma particles, you have to remember that it is related to the magnetic mirroring concept. Okay, this trapped, confinement or reflection, these are all same. The only alternative which is left, if this condition is not satisfied, like theta naught is less than 90 degree, then you can find out that what you call the particle or the plasma particle is lost completely. Okay. Again, if we go, which of the following is used for this confinement? Not the electric field. Plasma bubble is not the concept. It's only the magnetic mirroring. Okay. The next question is a natural phenomena characterized by appearance of streamers of reddish and greenish lights in the sky, especially near the polar regions, which is very important here. See, any natural phenomena which gives light in the polar regions, it has to be aurora. It cannot be lightning. Lightning is related to the thunderstorms. So it is, this possibility is going, and it is not the reddish or greenish light. Okay. Next is sprites. It is not being discussed properly. Air glow. Air glow is the phenomena which you can see in all latitudes, but only aurora is the one of the phenomena which we can see only in the polar regions. So that's why aurora should be the correct option, and the key word through which we can get to the answer is these polar regions, which is very important. So I just write it. So this is I think the seventh question. So, any natural phenomena giving streams of reddish or greenish light in the polar sky is actually aurora. Okay, and air glow you can see in all latitudes. We have distinguished between aurora and air glow in the previous session, so you can check that out. From there only many assignment questions people can solve. Okay, the next is another fact-based question. The air glow is measured in the unit of Rayleigh. So one Rayleigh for a column of height of 1 centimeter is equal to 10 to the power 6 photons per centimeter cube second, which is written quite well in the PPT of that particular week, that is week 12 PPT. You can see the last lecture, I think. There you can easily see one Rayleigh is defined already as 10 to the power 6, I think, no? Yeah, 10 to the power 6 photons per centimeter cube per second. This is the definition, so you cannot must not devote too much time to this. Okay, another thing is the ninth question: which of the following atom or molecule emits the red line at 630 nanometer, appears in air glows and auroras? It is the atomic oxygen, which is the correct option. And let me draw the diagram again. I have drawn it in the previous class. Let me draw it again. This will be helpful in understanding that from which, actually this is the quantum energy jump through which they get this particular thing. So you have actually two equations are there. One is this oxygen, this atomic oxygen. 1s is the state. It is the quantum energy state from where, if the oxygen atom or this this atom jumps to D state, it liberates 557.7 nanometer, which is nothing but the green line. Okay, green line emission. And another equation is, if from D state, if this atomic oxygen goes to 3p state, it will give out 630 nanometer, which is nothing but the red line emission. Okay, this is the red line emission, and if you just draw the states, it will be very good. So this is the thing. So 3p states, so like this. Okay, so it is 0, 1, 2. This is the 3p state, and you have, this is 1d state, and this is 1s state. Okay, so now if an atom jumps from here to here, it will liberate out h nu, which is green, right? From S state to D state, 557.7 nanometer wavelength is released, wavelength photon is released. And again, if from 1D state it goes to, say, the last state, so it liberates out h nu, a photon whose wavelength is 630 nanometer, which is the red line emission. So this is the concept of the, whether it is air glow or aurora, you will find the atomic oxygen which gives the red line at 630 nanometer. In fact, green line is also given by that only, but the jumps are different. The last question is the polar lights. Again, see, the polar lights are related to the aurora, especially appearing in green, red or blue colors, which are mainly produced by, it is again a fact-based question, it's oxygen and nitrogen which produces this. Particularly this nitrogen is corresponding to blue color, and this green and red is related to oxygen, which we have seen. So, okay, so just I will write that nitrogen and oxygen are responsible for blue, red and green color. You can also check that which molecule in aurora gives which color. Okay, so this will be helpful. Maybe this kind of question may come, but may not. There's a chance, very less chance that this kind of question comes. But it's good to know that which molecule is giving which kind of color in the aurora. So why we are talking about aurora? Because they have said that it is a polar lights. Polar lights are mostly related to the aurora. So okay, now we have already solved the 3rd, 4th, 6th, 7, 8, 9, 10. So all the 3 numericals are left. So I will just go to the next question, the next assignment questions as the numerical questions. And after these 3 numerical questions related to this week 12 assignment, now this 12th assignment will be complete, and after the 12th assignment is complete, we will go to the previous year assignment questions, which I have not solved so far. Maybe 2-3 questions I have solved. It will be good to revise it again. So this is the first question of the assignment. It states, if the Earth's magnetic field is B naught is given 3 into 10 to the power minus 5 Tesla at the equator and falls off as this, a particular functional form in the radial direction is given, and whose B naught is given as 3 into 10 to the power minus 5 Tesla. Of course, that will be the unit, because r cube will cancel. The units of r cube will cancel. And I need to find out the drift velocity, the gradient B, V grad B, of a photon of energy. The kinetic energy is already given, and at what distance they have mentioned that it should be 5 equatorial radius. So in the equatorial plane will be what? So the V gradient B we need to find out. So to find, let us write first, to find V gradient of B. Okay. We know the formula of V gradient of B. The way we have seen, that is in the y direction we have the gradient. So based on that, whatever we have got, let us write that. So it is minus the kinetic energy times delta B by delta y divided by q into b square or bz square, which way. But here B is given, but you can see that B will have only the radial component, this gradient of B. So here we can see that magnetic field, or rather than writing magnetic field, let me write it. Here, gradient of magnetic field, gradient of B, let us write gradient of B, is only in R direction, right? Why? This is because if you take the gradient in, let's say, cylindrical coordinate system, then what you will get? It will be only delta B, delta R cap in the cylindrical coordinate. Suppose I am going in the cylindrical coordinate. You can take spherical coordinate, any coordinate you take. So cylindrical coordinate, for simplicity I am taking, plus 1 by R delta B by delta phi. Is B a function of phi given? No. Is B a function of Z? No. Therefore, the only possibility is that it is only delta B delta R. Right? So I will replace this delta B delta Y, which is nothing but the gradient of B. I will replace as, so V gradient of B, in this particular case it will be kinetic energy times delta B delta R, not Y, because Y is not given. There is no chance that we can write Y. Okay, and divided by Q and B square. Simple. This is the formula, and from in the formula, based on the above question, we have changed certain things. Now what we need to calculate, see, kinetic energy is already given. I have been told that this is a proton. See, this is a proton of energy. So this proton, its charge is already known. So the circular things are already known, but which is not known is this, the delta B delta R and the B square, although the formulation is given. So we have to calculate these two things, but whatever is given, let us write that particular thing. So given is this kinetic energy, which is 1 electron volt. What do you mean by 1 electron volt? 1.6 into 10 to the power 90 joules, right? Okay. What is the charge of a proton? It is again 1.6 into 10 to the power minus 9. Sorry, this is the minus 90 coulombs. Why? Because it is a proton. Proton and electron has same charge. Okay. Fine. Now these two things are given. Now things which are not given, now we will see. Okay. First is we have to calculate what is delta B delta R. So it is nothing but delta R of B naught R E cube by R cube. Okay. So function is R. RE is constant. R is the equatorial radius, which is 6,400 kilometers, the radius of the Earth. Okay. So B naught is also constant. RE cube is also constant. Let us take it out. So it will be what? Delta R of 1 by R cube. Now if you do it further, so it is B naught RE cube. So what it will be? Minus 3 divided by R to the power 4, isn't it? This should be the delta B delta R. Now I need to calculate where this delta B delta R at R is equal to 5 RE. It is given. So let's do it. Okay. So let's do it. Delta B delta R at R is equal 5 RE will be equal to rub it and again. So delta B by delta R at R is equal to 5 RE can be written as, therefore, what is that? Minus 3 B naught RE cube, which is already there, and divided by R to the power 4. So it will be 5 RE to the power 4, isn't it? Minus 3 B naught RE cube divided by that. Yes. Oh, just further, let us simplify it. So it is minus 3 B naught RE cube divided by, let us write 5 to the power 4 and RE to the power 4. So this RE cube can be cancelled and it will be only RE. Let us write it further again. So it's minus 3 B naught divided by 5 to the power 4 into RE. That's all. So delta B delta R we have already found out. Fine. Now let us again, okay, now another thing is the B. What is B? B naught RE cube divided by R cube. Now it should be B naught RE cube. Now in which place you have to write? This R is equal to 5 RE. So it will be 5 cube RE cube, isn't it? Right? So now this RE cube can be cancelled. Now what we need is B square. So it will be B naught square divided by 5 to the power 6, isn't it? So now this B square I have found out, delta B delta R I have found out, isn't it? Just put it into the formula. So what was that? V gradient of B, again just write down the formula. It's minus kinetic energy times, see this minus is not very important, you can take a modulus if you want, because we are calculating, we are interested in the magnitude, not in the direction. This negative is representing some direction, okay? Or if you don't want, here the negative sign will cancel out, so it does not matter. But you always try to take a what you call as your modulus. So 3b naught divided by 5 to the power 4 Re and b naught square. So b naught square into 5 to the power 6, and there is a q. So negative negative I am cancelling out. B naught and this b naught is cancelling out. Re will remain as it is, 5 to the power 4, and this gives 5 square. So V gradient of B will be 1 electron volt, let's write joules, right, into 3 into 25 divided by, okay, 1 B naught is there. Oh sorry, first the charge, the protonic charge, that is 1.6 into 10 to the power minus 19 coulomb, and B naught, what is B naught? 3 into, what was the value? 3 into 10 to the power minus 5. Let's write 3 into 10 to the power minus 5, right, into, and Re is also there, so it is 6400 kilometer. So I am writing 6.4 into 10 to the power 6 meters, right? Why? Because Re is 6400 kilometer, so it can be written as 6400 into 10 cube meters, which I am writing as 6.4 into 10 to the power 6 meters. This is the what I am writing. So this kinetic energy and Q will be cancelled out because they have same value. 25,375 divided by 3. Oh, this 3 was cancelling out. So let's directly write it 25. Okay, and well, this is 6.4, and 10 to the power minus 5 and 6 becomes 10. So I am writing it 10 to the power minus 1 in the numerator. So 25 by 6.4, if you calculate, let me calculate it out. It's something near 4, of course. 6.4. Yeah, 3.9. So it's 3.9 into 10 to the power minus 1 meter per second. So it will be 0.39 meter per second. Therefore, this V grad B, the drift velocity in magnitude, the speed actually is about 0.39 meter per second. Now, if you look at the answer of the first question, it was, as I remember, yes, it is 0.39 meter per second. Okay, so it's a good question to solve the drift velocity. Okay. The next question is a 100 kilo electron volt alpha particle. Now they have given alpha particle, its energy is also given. Okay, when an alpha particle is given, when it is proton and electron, it is fine. Electrons mass we know, protons mass we know, protons charge we know, electrons charge we know. But in case of alpha particle, we have to always be careful that, let me write it, alpha particle, we can miss this particular concept. So alpha particle has 2 times the charge of electron or proton. So it is 2 into 1.6 into 10 to the power minus 19 coulomb. This is the charge of the alpha particle, and mass is actually 4 times the mass of the protons. So it is about 6.64 into 10 to the power minus 27 kgs. Okay, you can just see it's just 4 times, because 1.67 into 4, if you do, it is kind of that. Okay, this is a large mirror fusion device where this capturing and trapping or losing takes place. So it is given that the pitch angle is 30 degrees, has a pitch angle 30 degrees at the mid plane, where the magnetic field is also given as 1 Tesla. What will be the Larmor radius of the particle B? So see, this kinetic energy of the alpha particle at a particular pitch angle is given. So I don't need to further put the pitch angle. I know that Larmor radius is nothing but that radius of gyration. Okay, and that is nothing but mv perpendicular upon qb. Now if you think that V perpendicular, again we write it as V sine theta, that's true, but when it is given as, so if you do it in kinetic energy term, it will be 2m kinetic energy divided by qb. Now this kinetic energy, that 100 electron volt which is given, is already included this 30-degree angle. So I don't need to further include that because it's only the scalar quantity, the kinetic energy. Okay, so it's just R, which is nothing but, we have solved so many times this kind of question. It's 6.64 into 10 to the power minus 27 into the kinetic energy for 30 degrees angle is given as 100 into, see, is kilo, so it's 10 cube into 1.6 into 10 to the power minus 19 joules, right? And whole divided by Q. Q is what? Remember 2 times, yes, 1.6 into 10 to the power minus 19 coulombs times magnetic field is 1 Tesla. So don't put 30 degrees until and unless it is mentioned that that here, see, this is already mentioned in the question that 100 kilo electron volt alpha particle in a large mirror fusion device has a pitch angle of 30 degree. So no requirement to include that 30 degree. It's already included. So its kinetic energy is already having this 30 degree pitch angle. So we don't need to consider it again. It's just the Larmor radius formula. Just put the formula and get the result. That's all. Okay. So if you just do it, let me calculate it some. Let's write it like this. So it's, sorry, 2 into 6.64 into, let's write it 10, so minus 27, and it will be 10 to the power 4, and then so it will be 10 to the power minus 15, because 3 plus this, I have written here 10, so 1 0 is taken care, 10 to the power 4, so it is 10 to the power minus 15 divided by 2 into 1.6 into 10 to the power minus 19. So if you do it, it will be 2 into 6.64 into 10 into 10 to the power minus 42. Okay. Now you take the root divided by, again this is 3.2 into 10 to the power minus 19. So now it can be written as root over 2 into 10 into 6.64, and I keep that out, and there is a, in the denominator it is 10 to the power minus 19, so I am just adding it in the numerator divided by 3.2. Now if I solve this particular thing, it comes out to be about 14.64 divided by 3.2 into 10 to the power minus 2, which comes out to be about 4.56 into 10 to the power minus 2 meters, which comes out to be about 4.56 centimeter. So this should be the answer. Okay. Now, yeah, it is about 4.5 centimeter. Okay, next question is, which is the last question of the assignment so far what we have solved. Calculate the magnetic moment of a gyrating electron having kinetic energy 100 kilo electron volt at an angle of 45 degree with magnetic field 5 into 10 to the power minus 5 Tesla. So I know from the magnetic mirroring a formula which relates the magnetic moment, the kinetic energy is equal to sine square theta by B. Okay. This is the, actually in the magnetic mirroring case, this is actually constant with time, this is also constant with time. So this sine square theta by B is actually constant. This is the formula which we have got for magnetic mirroring case. Just you put values over here and calculate the magnetic moment. This is what we need to find out here. Okay, so mu will be equal to Ke sine square theta divided by B, right? So this kinetic energy is 100 into 10 cube into 1.6 into 10 to the power minus 19 joules into sine square 45, so it's 1 by root 2 whole square, right, because sine 45 is 1 by root 2, and divided by 5 into 10 to the power minus 5 Tesla. So what we can do here is that okay, so this becomes 10 to the power 5, right? So 10 to the power 5, and this is 1.6. 10 to the power 5 minus 19 is 10 to the minus 14 into half divided by 5 into 10 to the power minus 5. So it's becoming 0.8. Okay, and so this, now if you just do one thing, make it 80, make it 80. So what it will happen, it will be 10 to the power minus 16, right? Yeah. Plus 5 is there, divided by 5 is also there, so 5 into 16 is 80, so it is 16 into 10 to the power minus 11, or it will be 1.6 into 10 to the power minus 10, and unit will be joules per Tesla. Right, so this is the answer, I think, in the last question. So we just check once. Yeah, it's 1.6 into 10 to the power minus 10 joules per Tesla. Fine. So we have solved all the assignment questions. This is the numericals which we have solved. This is the longitudinal drift. We have talked about that. Magnetic moment is the invariance in this magnetic mirroring concept, and magnetic mirroring based questions are also there, and aurora based questions are also there. One Rayleigh you should remember, it is 10 to the power 6 photons per centimeter cube second, and oxygen and nitrogen are responsible for production of lights in the polar region, and mostly atomic oxygen is responsible for producing that green emission, green line emission and red line emission. Okay, so this ends the assignment discussion. Now no further concept has to be studied because no further weeks are there. So what I have done is that from the previous year assignment questions, I have chosen certain questions, particularly these two numericals I have not done, so I will do it today, and some questions which I have missed, those questions also I will solve. These are the previous year assignment questions, and these two questions I think I have done already, solved already, but I have again kept it so that this concept will be revised and we will end up there. Okay. Just a minute. Okay. Fine. So the question says, this is related to that atmospheric part, not the space part. Space part we have discussed so many things in the last couple of lectures. So these are mostly new, and all the assignment questions in the previous year which are there, they are mostly repeated. So we have solved all that, all of them in the assignment questions from week say 9 to 12, 8 to 12. Before that, certain questions were missing, so those questions were I will solve today. Okay. it is given that the it has to be calculated that calculate the average density of the layer between 700 MB and 500 MB if the height of the 700 MB surface is given and the height of 500 MB surface is also given. So what we have to find out is the average density of that particular layer. So suppose this is 500 MB, this is 700 MB. We know that pressure decreases with height, so that's why the lower pressure will be at the higher height and higher pressure will be at the lower height. So this, its corresponding geopotential height is 2898 meters, and for 500 MB it is 5370 meters, right? Now I need to find out that here in this region what will be the average density. So looking at these things, see, you have been given the Z, the difference in the height between these two pressure level. You have been given the difference in the pressure level, delta P. Now what is the relation through which this delta P and delta Z is related? The only relation which will come and will relate this delta P and delta Z is nothing but the hydrostatic approximation. So hydrostatic equation, let us write. So hydrostatic equation is what? It is the balance of the vertical pressure gradient force and the gravity. So it is nothing but dp dz will be equal to minus rho into g, and this rho is the average density of the column. So this rho bar I need to find out. Given is dp is given, dz is given, and g is constant, we know. So what is this rho bar therefore? This rho bar will be equal to minus dp by dz 1 by g, right? So minus the change in pressure, so it will be 500 0 I am also writing because I need the density in kg per meter cube because nothing is been mentioned here, okay? And 700 0 I am converting it into pascals, so 1 millibar is 100 pascals, or 1 hectopascals is 100 pascals. Remember this thing, okay? And this dz is 5379, corresponding to 500 MB is 5379 minus corresponding to 700, it is 2898 into 1 by 9.81, correct? Now you take out this take the minus sign inside, so what you get is 200, because 500 minus 700 is 200, 0 divided by the difference between these is about 2472 into 9.81. So if you calculate it, let us do it. It is about 200 divided by 2472 divided by 9.81. It is 0.82 kg per meter cube. Remember, the air density of the air is about 1.028 kg per meter cube. So you can compare whatever your value. It should not be very high. Say if you are getting about say 10 kg per meter cube, it is not possible in a particular atmospheric layer. It of course may be possible if the composition of the atmosphere is different, but in this case it is not possible because it is simple air based column which they have mentioned here. Okay. So it is 0.82 kg per meter cube is the average density. So in the previous assignment, previous year assignment, it was given in a numerical type question where you have to write the solution, but the answers which are given is wrong because they have given it in meters. So I think it is, they have just mentioned this difference in the height, which is not a part of a question, but given is to calculate the average density. So the answer was wrong, but this should be the correct answer for the average density. So what we have used here is we used here the hydrostatic equation. So remember again, the hydrostatic equation is the balance between the pressure gradient, vertical pressure gradient force and the gravity. So this is the concept here. Fine. The next question is somewhat complicated but still can be done. It is given that two balls of diameter 4 centimeter are placed 100 meter apart. So let's draw two balls which are kept at 100 centimeter apart. Okay, sorry, 100 meter apart. Yeah. Diameter is 4 centimeter. So this is 4 centimeter. This is also 4 centimeter. In frictionless horizontal plant at 43 degree, let us consider it to be in the northern hemisphere. It is given. Okay, so phi, the latitude angle is given to be 43 north. If the balls are impulsively propelled towards each other with equal speed, very important is that impulsively propelled means they are moving in the opposite direction with equal speed. At what speed? That equal speed is what? Where they should travel so that they just miss it. So just miss means what? If you just make it, see, at 43 degree north, if they are moving with a particular velocity and earth being a rotating frame, so what will happen? They will get a Coriolis force. So as a result, this ball will come here and they will just miss. So what will be the distance from the center of one of the balls? It is about 2 centimeter. Right? So just miss condition is the distance is about 2 centimeter. Then only it is just miss and pass. Okay. So and the concept here is in the rotating frame, rotating frame means accelerating frame or accelerating frame, which is in this case the earth, which is obviously rotating earth, then any object having velocity will experience Coriolis force to its right. Why right? Because it is in the northern hemisphere. It would have been left. It would have deviated left. I have see this is the original position of the ball. Now it is going like this. So it has moved towards its right if it is moving in this direction, right? So this is because it is in the northern hemisphere. Coriolis force always deviates any particle or winds in the northern, towards its right in the northern hemisphere and towards its left in the southern hemisphere. Okay, so this is the concept here. Fine. So finally it should be 2 centimeter when it just misses it. Okay, now what will be the separation distance in the beginning? So you can see that equal speed they are moving, so they will cover equal distance in a particular interval of time. So 2x should be equal to 100 meter. So x will be equal to 50 meter. Okay, because they are moving in equal speed. So equal speed. So that is for same delta t, each of the balls will move this amount. Okay. Fine. Now let us do one thing. Let us find out the time. Okay, the time which it will require to cover this particular thing. So the time, Okay, let me just start with the basic equation. So the momentum equation is dv dt, or the acceleration, will be equal to the only force which is present here, because it is frictionless, everything is not there, no pressure gradient is there. So dv dt should be equal to the Coriolis force in the which direction? Because see, if a particle is moving in this plane, its perpendicular plane will be the direction of the Coriolis force. So if I am writing say some dv dt, so it will be minus 2 omega u sine phi. You can do it using this omega cross v thing, minus 2 omega cross v. You can find out that this is the Coriolis force. Okay, now so dv will be equal to minus 2 omega u sine phi dt, and just I will write that v will be equal to minus 2 omega u. We will assume that initial velocity is 0, sine phi into time was also 0, and so it's t, right? So what will be y therefore? Because this v will be what? Dy dt again. So if we integrate it, so it will be 2 omega u sine phi t square by 2, right? This 2 will be cancelled out. Now what is this u? This u is nothing but x by t. I know that because they are moving in equal velocity, so x I have found out to be 50 meters, so it will be 50 by t, right? So just if I write y will be equal to, just take the modulus, omega 50 sine phi by t, so t will be cancelled out, so it will be this. Okay, now so I need to find out this t, then only we will find out at what velocity, at what speed should they travel. So this u need to be found out. Okay, this to be found. So for that, let's calculate the time. So how will we calculate the time? So finally, that is the just miss condition. We can write it. So t will be equal to y divided by omega into 50 into sine 43. Correct? Now I just take another slide. So required here. Yeah. So now this time can be written as, so finally the y is how much? 10 to the power minus 2 into 10 to the power minus 2. Why? Because 2 centimeter. See, this is the y, right? Because let me again show you. This is the initial thing, 100 meters apart, moving with equal velocity. So each of the particle in a same time will travel 50 and will come here, and at that time the separation is 2 centimeter, because that is the only diameter. So this is the y and this is the x, right? And the Coriolis force is acting in this direction continuously. Okay, so now what will happen? This is the final situation, and from the final displacement, which is in the y direction, not in the x direction, that I have written divided by the omega that is known to us is this, into sine 43 into 50, and if you calculate it out, it comes out to be 8 seconds. Okay, and what we require to find is u. What is the velocity with which it has started, or the equal velocity is what? So u will be equal to x by t, and we know that since they are oppositely moving with same velocity, so 2x will be equal to 100 meter, so x will be equal to 50. So this is the 50 meter divided by 8 seconds. This should be the answer. That comes out to be 6.25 meter per second. That's all. Fine. So this is the concept. It's kind of a complicated concept, but it's very easy to understand if you properly see it. So this is the momentum equation which I have used in the y direction. Why? Because the displacement is happening in the y direction because of the Coriolis force, right? And what is the displacement? So that it just misses. So that is the 2 centimeter, because one ball is just over the another ball, right? And in this way we have found out y, but we don't know u. This u has to be found out, but it is given that they are moving towards each other with equal speed, so we can find out the distance at the same time. So distance is found out, time can be found out using the final displacement. So in this way we have calculated that the initial velocity of the balls, because both the balls are moving in this, so this is 6.25 meter per second. Fine. Okay. Now certain simple questions are there. We will just discuss and wrap it up. Fine. So this is the virtual temperature depends on what? So there is many things are given: moisture concentration, dry air temperature, dry air concentration, etc. and so on. So the correct option here is given to be moisture concentration, but I disagree with that, because dry air temperature is equally important, and dry air concentration, well, to some extent is important, but since if we write the expression of the virtual temperature, it will be getting clear. So if it had been said that the virtual temperature gives what, well, I would say that it will tell us about the moisture amount present in the atmosphere, but this is not the thing. It has been said that it depends on. So let us just slowly derive that virtual temperature expression. Will be helpful for you to solve numericals also again. So it's a revision. So for the moist air parcel, so it's always for the moist air parcel, very important, for the moist air parcel. So what we have seen, dry air parcel we have seen, vapor we have seen, and this is the moist air parcel. So this is for the moist air parcel, where we have seen that the equation of state, or the ideal gas equation, looks like something like this: 1 plus R by epsilon, where R is the mixing ratio. Okay. This R is nothing but the mixing ratio. What is this mixing ratio? This mixing ratio R is nothing but rho V by rho D. This is the density of the vapor, and this is the density of dry air. And this R is actually a function of temperature as well as pressure. Now this mixing ratio gives the moisture concentration. Dry air concentration is not required, because it already consists that in 1000, what is the definition? So if you see the definition, says 1000 grams of dry air, how much vapor? Dry air, how much vapor? This is the definition of a mixing ratio. So this will give the moisture concentration. So it depends on the moisture concentration, and so virtual temperature is actually this thing. So this TV, the virtual temperature, is nothing but T of 1 plus R by epsilon divided by 1 plus R. Now if you further simplify this expression, this becomes 1 plus R by epsilon, 1 plus R to the power minus 1. Binomially expanding and neglecting higher order terms, we have 1 minus R. So if you just do it, R is a small quantity, as you can see that denominator, if you have 1000 grams, so it's about 1, I think it is this R by epsilon is 1.609 R minus minus R and minus 1.609 R square. This is 0, we don't need it, so it will be T 1 plus 0.6 R. So what this virtual temperature is dependent on? It depends on, of course, this dry air temperature, and depends on the moisture concentration. So only moisture concentration should not be the right answer. But if the same kind of question is given in the exam, just write the moisture concentration. But dry air temperature is also one of the options. And if all of these or something kind of thing comes, then that will be the most appropriate thing as per my suggestion. Okay, so we have discussed some concept of the virtual temperature only related to the moisture parcel, depends on dry air temperature as well as the moisture concentration. Fine. Okay. The next question is, the heat supplied to ideal gas at constant volume is equal to. So heat supplied to ideal gas. So let us write see this is the heat supplied and it is at constant volume, something related to the first law of thermodynamics. So if we write the first law of thermodynamics, what it will be? Writing in the specific term. What is the meaning of specific? Per unit mass. So it is Cp, let's write it like this, Cv dt plus Pd alpha. Why am I writing? See, there is another expression which is delta Q, which is equal to Cp dt, mostly used in meteorology or atmospheric science, is this. Why am I not using this but using this? Because you can see that heat supplied to ideal gas at constant volume. So if it is a constant volume, so d alpha will be 0. That's why I am using this, not using this, because there is nothing which we can put 0. Okay, so delta Q will be what therefore? Delta Q will be Cv dt. And what is this Cv dt? It is nothing but the change in internal energy, right? Now, thoroughly look at the question. Heat supplied to the ideal gas at constant volume is equal to. Is it equal to the change in temperature? No. It is not equal to the change in temperature. Now, had it been said that it is dependent on, like the previous question, it is dependent on, of course this is the correct option, change in temperature, because delta Q is dependent on change in temperature, which we can see it from here, right? Change in pressure? No. Change in internal energy? Yes. This is the only thing. And it is not 0. So, it is the equal to the change in internal energy. It's just a simple physics thermodynamical question, very basic. Just require the expressions of the first law of thermodynamics. Don't confuse between these two expressions. These two expressions are same thing, but whenever we require in a particular way, we will go in that particular way. For example, here is a constant volume, you have Pd alpha like expression. So you just put it 0 and you understand the concept from there. Now, had it been seen that at constant pressure, then we would have taken this. And then what will be the consequence? This dP will be 0. What is this? This is the change in enthalpy. This is change in enthalpy. So for isobaric process, for isobaric case, the change in heating is actually equal to the change in enthalpy. But for isochoric, which is this constant volume, you have change in internal energy. So remember this also. This is also important. Maybe that this question is replaced with some other question like this. Say for constant pressure, what will happen? So this is the change in enthalpy. Fine. Okay. The next question is that on moving from middle latitudes to tropics, mixing ratio in the atmosphere. Now, not much to say here, see, mixing ratio always increases in the tropics. Why? The reason is moisture. In the tropics you have huge amount of moisture. Why we have huge amount of moisture? Because in the tropics there are oceans which are present. Of course lands are also present, tropical land is also there, but ocean is also present, that gives the moisture. Another thing is there which is giving the moisture, that is your high temperature. So you will remember that we generally say that tropics is having specific characteristics of high temperature and high relative humidity. High relative humidity means moisture is high. So what happens is that in the tropics you have oceans, abundant oceans. So as a result evaporation takes place. Why evaporation takes place? Because of high temperature, because evaporation depends on temperature. So as the temperature increases, more vapors, and we have seen that warm air can hold more moisture. Why? Because I have discussed it. So warm air has high because temperature is high, your kinetic energy is also high. So kinetic energy is high means it can easily collide with the vapors. The nuclei, condensation nuclei will easily collide with the vapors. So collision with vapor molecules lead to condensation. Hence it carries more moisture. So warm air carrying more moisture, and we know that mixing ratio is nothing but rho v by rho d. So more vapor if an air consists in the dry air, then its mixing ratio also goes up. So mixing ratio will increase, it will not decrease, it will not remain constant, it will not become zero. Okay, so this is the simple concept. I have gone somewhat deeper, like the temperature increases, kinetic energy increases. So this is the CN, the condensation nuclei. So condensation nuclei will have a huge amount of motion. So this motion will result into collision with the vapor molecules and lead to condensation. So more water molecules or more vapor will be there. That's why the mixing ratio increases in the tropics. Okay. So far we have discussed the virtual temperature question. We have discussed something related to the first law of thermodynamics. We have seen that in different processes what will happen, and then we gone to a very basic fundamental question, that what will happen to the mixing ratio. In the tropics we have to remember that it has high temperature and high humidity. Humidity is related to the moisture, so mixing ratio will be definitely increasing. Next question is, the internal energy of the sinking air parcel will be what? What will happen? I will just pose the question in opposite way, that the internal energy of a rising air parcel, what happens? So you will remember, I will again discussing it again, so it is a revision kind of. So in the surface, suppose you have an air parcel. Air parcel does not require to be this circle or elliptical like that or spherical like that. It can be anything. It can be a point also. Okay, this parcel has no shape. It's just our imaginary thing. Now this has a particular temperature. Now as it goes up, it has a pressure also. Okay, now as it goes up, pressure in the environment decreases. We know that pressure decreases with height. But in the parcel, it is remaining same, but it cannot be possible. It has to come in equilibrium. This is the law of the parcel theory. So if it has to come in equilibrium, then what will happen? Pressure has to decrease. So if the pressure has to decrease, then the volume will increase. So how the volume will increase? Volume will increase volume will increase so that pressure within the parcel becomes equal to pressure in the environment, right? Now, so for that, what is happening? Volume will increase. Now, how the volume will increase? It cannot do by its own, so work will be done. Work is done for increasing the volume. Now, if work is done for increasing volume, then where is it getting energy from? So, work is done by losing the internal energy, right? Now, this internal energy, as we have seen, is CVDT. If it is decreasing, then what will happen? Temperature decreases. But remember, this is the case of rising parcel, right? This is the case of the rising parcel. Then for sinking parcel, what will happen? Just the opposite. Earlier it is here, now it is going down, so pressure is increasing, so here the P is increasing. To come in equilibrium, volume will decrease. So work will be done on the parcel will increase internal energy. If it increases the internal energy, temperature also goes up, right? So the internal energy of the sinking air parcel will not remain constant, will not be decreasing, it will increase, it will not become zero, right? So this is the concept. Just remember this rising air parcel, sinking air parcel will be exactly opposite. Okay, for rising air parcel, internal energy decreases, but for sinking air parcel, which is given here, it is increasing. Okay, this is also an important concept because I remember some assignment questions were there based on this particular thing, so it may be a good concept. Okay, next is, which of the following does not help in convection of air? Now, if we just list down what we have studied for convection, then it will be helpful in understanding or answering this question. So different convection types, we have listed several convection types and discussed it. So first one, what we have discussed is some low pressure. If there is a low pressure, then there will be convergence of air. Okay, convergence of air at surface. So what is this low pressure is meaning? Meaning is that suppose this is a low pressure, outside will be high pressure, so winds always blow from high pressure to low pressure, so winds will come in from all direction. So if it comes from all direction at the surface, then it cannot go down because there is a surface, so it has to go upward, and this is how the wind moves up and condenses and form clouds. So this is number one. Number two is frontal convergence. Again a convergence. How this frontal convergence? What is a front? Two air mass. Suppose there is a cold air mass and there is a warm air mass. We know that warm air mass is lighter and this is denser. So when they are moving opposite to each other, what will happen? The colder air mass becomes like this, warmer air mass goes up. This is the kind of a frontal convergence. This is the lifting or frontal convergence or lifting, you can say. Okay, so this is the front. Okay, the third one is thermals. What is that? Tremendous surface heating. What it will do? It will heat up the surrounding air. As a result, what happens? As the temperature increases, density decreases and it goes up. Parcel goes up, which we call as thermals. And the fourth is orographic lifting. Orographic lifting. What will happen? Suppose you have a topography, winds are coming like this. Okay, after striking this, it cannot go back because there is a continuous force which is coming. So the wind has to go up. So this upward upliftment of winds or air is nothing but convection, right? And if you now see the options which does not help in convection of air, see surface heating, it is helping, which is related to these thermals. Topographic lifting, it is, which is related to this orographic lifting. Convergence of air, these two is actually giving the same thing, but divergence at the surface is not the what you call as not the process of convection. Why? Because divergence takes place. Divergence means all the winds are going out from this particular place. So it generally happens when there is a high pressure system. So high pressure winds will be divergent. So this does not result into convergence. It will result into sinking motion. Okay, so let me write the answer with some different sign. So this is the this is the correct option. This is not, this is not, this is not. Okay, fine. Right. So we have talked about the convection also. So that is also now clear. Okay. Some more questions are there. Yeah, let's do it. The condensed air parcel cools more slowly because of. Condensed air parcel cools more slowly because. So you have a condensed air parcel. Suppose this is the air parcel at a greater height, of course, because condensation has already taken place. So you have, in a condensed air, you have condensation droplets, you have some dry air, of course, and some saturated vapors. So it consists of saturated vapors, it has some condensation droplets, and it has some dry air. Now, whenever this saturated vapor is transforming itself to condensation droplets, what is happening? Phase change is taking place, so latent heat will be released. Heat released. Now where this latent heat will go? So this is a parcel, and parcel follows adiabatic process. Right? If it follows adiabatic process, latent heat will remain. Latent heat which is released will remain in the parcel, and this will not allow the condensed parcel to cool fast. So it will cool slowly. So this should be latent heat. This is the correct option, not the internal energy increase, temperature increase or pressure increase. This is the option. Fine. Okay. The next question is about some thermodynamic adiabatic process. Just a minute. Okay. The next question is, which of the following thermodynamic quantity remains a constant during adiabatic process? Is it temperature? Is it pressure? Is it volume? Or is it potential temperature? Now see, just by knowing the physics of thermodynamics, we know that each process has a proper name, right? If temperature is constant, then it is isothermal, right? Which is not adiabatic, of course. Pressure, constant pressure process is isobaric. Constant volume process is isoporic. So nothing is related to adiabatic process. The only option will be this. So this should be the correct option. We know. Okay. But how will you prove it? Which is not required in this MCQ based question. But if you have to prove it, if you have to know why is it so, then from where should we start? We should start with the adiabatic process. What is that? We know that P alpha to the power gamma is constant for an adiabatic process, where alpha is the specific volume. I am not writing PV to the power gamma, I am writing alpha to the power gamma, just specific volume. Gamma is CP by CV, right? So P alpha to the power gamma is constant. So let's say K. Okay. Now I apply ideal gas equation. So it's RT by P. I can write gamma is equal to K. Okay. So P 1 minus gamma R T to the power gamma is K. Okay. So P 1 minus gamma T to the power gamma is K by R. Let us write it. It's a K1. New constant because R is also specific gas constant. Okay. Next, what I do is that P1 minus gamma divided by gamma. So I am just dividing the powers by 1 by gamma. So it will be K1 to the power 1 by gamma. That is nothing but K2. Now, P 1 by gamma minus 1 into T is K2. Now P, can I write it CV by CP minus 1 into T is K2, isn't it? So P CV minus CP by CP, this is all in power, remember it's all in power, into T is K2. And what we can write, CV minus CP is P minus R by CP into T is K2. Right? Now remember the potential temperature expression. What is that? Theta is equal T P naught divided by P to the power R by Cp. Now this P naught is 1000 MB, is always constant as per the definition. This is constant. Therefore, can we write theta is equal to T P to the power minus R by Cp into some constant? And T into P to the power minus R by Cp is nothing but K2. So it is constant times K2, which gives you K3, which is nothing but a constant. Therefore, theta, the potential temperature, remains constant. Right? We have proved it. There are many ways of proving. This is one of the ways of proving. Fine. So which of the thermodynamic quantity remains constant during adiabatic process? It is the potential temperature. Of course, by guessing, you can easily put that temperature is, if temperature is constant in adiabatic process, that is isothermal. It is not possible. So it's only the potential temperature. right? Okay. I think 3 more questions are there, and some more questions are there. I have already solved those questions, but it will not take much time, so we can again solve it. But let's discuss this particular concept. This is very important. Okay. The next thing is that the Brand-Weisshaler frequency represents the sound waves in the atmosphere, stable atmospheric oscillation, unstable atmospheric oscillation, and planetary waves. Well, see this Brand-Weisshaler frequency. First of all, in the option, you are seeing that it is an unstable atmospheric oscillation. I will come to it. Let's write what is the Brand-Weisshaler frequency. Just I am writing the expression, which will be helpful even if you have to solve some numerical questions. It will be helpful, this formula. This is n square. This is frequency square actually. So G by temperature of the environment and gamma D minus gamma. This is what it is. Gamma D is the lapse rate of the parcel or the dry air, whatever you say. And this is for the environment. Same lapse rate. And the equation, vertical momentum equation, becomes n square delta z equals 0. Now if gamma D, gamma of the parcel, is greater than gamma, then n square is greater than 0. In that case, delta z double dot is plus n square delta z should be equal to 0. And we know that the solution of this is oscillatory. Why? Because you have a cos nt plus b sin nt. This is oscillatory. And gamma d, if it is greater than gamma, then what is happening? It is a stable situation. So stable atmospheric oscillation is definitely the correct option. Now you tell me, if n square is less than 0, delta z will be what? Or delta z double dot will be minus n square delta z, that is equal to 0. And what is the solution of this? A e to the power nt plus b e to the power minus nt. Now this is unstable situation. Of course, this is unstable situation where gamma d is less than gamma. Environment is having higher lapse rate as compared to the parcel. But this unstable is not the oscillation. It's just the rising or the sinking motion. So it's not the oscillation. So this is not the right answer. No planetary waves. Sound waves are called the acoustic waves. It does not depend on this Brand-Weisshaler frequency. Its frequency is different. So only option is the stable atmospheric oscillation. Okay. Fine. The next thing is about the lapse rate, which we can now discuss. If the environmental lapse rate is faster in comparison to the parcel lapse rate, the parcel displaced from the mean position will. Okay, let's just draw it. What is it? What has been said? Environmental lapse rate, which I am representing by gamma, is greater than gamma p. So what does it say? Let's make it. This is the temperature. This is height. What is happening? So for temperature, suppose this is how the lapse rate is moving. Why? Because gamma is nothing but minus dTz. Remember, this is the negative of dt. So rate of decrement of temperature. So that's why I am writing like this. Okay, this is for the environment. Now, just change the color for the parcel. For the parcel, it has been said that it is decreasing in a lower rate, slower rate, I would say. So this is the parcel, right? So this is your gamma p. This is your, sorry, change the color, gamma, isn't it? This is what it is following. Gamma p is less, gamma is more. In this case, you take any height. Here is the parcel, here is the environment. So parcel's temperature is high or low than the environment? Parcel's temperature of the parcel is greater than the temperature of the environment. In that case, what will happen? The density of the parcel will be less than density of the environment, because higher temperature means lower density. So if this is having lower density as compared to the environment, then due to buoyancy it will rise. It will rise. So which kind of situation it is? It is unstable situation. If you see the Brandt-Weissler frequency again, it will be G by TE gamma D minus gamma, or gamma P minus gamma if you write. So gamma P is less, so n square will be less than C. Okay. So it's an unstable situation. Fine. This is an interesting question. It says that dry static energy of an air parcel is gained energy, lost energy, it's a constant, or internal energy. Let's see. What is the dry static energy definition? DAC is nothing but CPT plus GZ. Okay. Now this air parcel generally follows adiabatic process, right? We have seen. Let us consider, since it is a dry static energy, let us consider adiabatic, and it is a dry process. So dry adiabatic process. And in dry adiabatic process, we remember dt dz is what? Minus g by cp, isn't it? Cpd or cp. Therefore, we can write cp dt is equal to minus g dz. This is the lapse rate. DALR, dry adiabatic lapse rate. Okay, so this is dz. So Cp dt plus G dz should be equal to 0. I take the d, the derivative, so it will be Cpt plus Gz. Can we write like this? Of course, because Cp is a constant, G is a constant, so it is like this only, equal to 0. D of, what is this? DAC equal to 0. Then what is DAC? It is constant. So for an adiabatic process, which is for the parcel, this DAC is constant. Therefore, DAC is constant. Other things are wrong. Okay. Now some two numericals. This I have already done. I am still again doing it. Will be helpful. Just give me some time. Okay. Maybe not this one. The next one I have done, but these are simple. Okay. An air parcel that has temperature of 20 degrees Celsius at 1000 MB level is lifted dry adiabatically. Okay. What is its density when it reaches 500 MB level? So just draw it. So this is 1000 MB level, this is the 500 MB level. Right? And 1000 MB has, this is 20 degrees Celsius. Okay? And a parcel is dry adiabatically lifted to this. Then C. Now it is dry adiabatically lifted. So it's a dry adiabatic process. And in dry adiabatic process, which thing is constant? We have just derived theta. Theta is the potential temperature. Of course, that DAC is also constant, but potential temperature is constant. Right? For dry adiabatic process, potential temperature is constant. Now, so what is theta? Theta is T Ps by P to the power R by Cp. Right? Now, if theta is constant, then at surface it should be like this: Ps by Ps, because the pressure rate at the surface, R by Cp, will be equal to T at any level. Say this is for the 500 level, R by Cp. We can write like this because this is constant. Correct? Now, what we will do is that we have to calculate the density. So we have to some way come to density. So you can see this PS is cancelling out, so it does not require. So PS upon rho S R. Okay, this is coming from where? Ideal gas equation. So let us write it. This will be P by rho R. Again, this is PS by P to the power R by C. Right? So I need to find out rho. So let us keep rho on the left hand side, and what I get is you have, of course, the rho S R divided by, so this is P, there is a R, there is PS, isn't it? And there is a PS by P to the power R by Cp. Fine. So what we will do is this R and can be cancelled, and so I can write rho will be equal to rho S PS by P to the power R by Cp minus 1, because P by PS is already there with a minus sign. Okay. Now rho S can be written as what? Again PS upon RTS, and this will be PS by P to the power R by Cp minus 1. And what is this R by Cp? It's about 0.28. So R by Cp minus 1 will be what? Minus 0.72. Okay. So now we write it. Rho is, surface pressure is 10 to the power 5, because we are converting 1000 MB is converted into 10 to the power 5 pascals. Okay. Divided by 287 for dry adiabatic. So it's our specific gas constant for dry air is 287. Again I am writing, helpful for you, 287 joules per Kelvin per kg. RV 461.5 joules per Kelvin per kg. Okay. So 287 into TS, what is that? 20 degrees Celsius, that is 293 Kelvin. Always change Celsius to Kelvin in thermodynamic questions. PS is again, now you don't need to change because it is in the ratio here, so it is minus 0.72. So it will be 10 to the power 5 divided by 287 to 293 half to the power 0.72. Just I am replacing the negative sign and doing it like this. So, 0.72. And if you calculate at 500 Kelvin, comes out to be 0.725 kg per meter cube. This is the answer. Okay. And after this, the last question so far, and after that just I will write certain formulation, and this will end up. If air contains water vapor with a mixing ratio of this and total pressure of this, what will be the vapor pressure? It's simple mixing ratio question. It's just epsilon E by P. You have to remember that R will be 0.622. This epsilon is 0.622. E divided by P. So E, which is the actual vapor pressure. Actual vapor pressure is nothing but P. P is what? 1026.8. Give it in hectopascals, it does not matter. But check the options. If the options are in pascals, then you have to convert it into pascals, into 100. Otherwise, you can leave it. If it is in millibar, then you can leave it like this. Or in hectopascals, you leave it like this. Okay. Sorry, this is wrongly written. P into R will be the thing. So R is 5.5 grams per kg. And have to be converted. So how much it will be? 5.5 into 10 to the power minus 3 kg per kg. There is no unit. So it is 5.5 into 10 to the power minus 3 divided by 0.622. If you calculate all of this, then it comes out to be about 9.07 millibar. So fortunately in the assignment question the option is 9.07 millibar, so therefore it is fine. Otherwise if it is in pascals then it will be 907. Okay. Now some key formulas, just I will write down some formula. I will not discuss too much, just the formula I will write, and this particle nature also. So in this, just a minute. Right. So in this Debye potential, the key formula is the what you call as lambda d, Debye that radius. So it becomes epsilon kb t divided by e square n naught. That is epsilon is the permittivity in free space, so 8.85 into 10 to the power minus 12. Okay, kb is Boltzmann constant 1.38 into 10 to the power minus 23 joules per Kelvin. Fine, and T is the temperature, of course. E square, E is the charge, and N naught is the number density or charge density. Right? So this is the Debye radius. Right? And just a minute. Let me check the formula once more. Yeah, this is fine. Epsilon naught kbt by n e square. So this is not Debye radius but Debye length. Okay. Further, number of particles in Debye sphere is given as lambda and is about 4/3 pi lambda d cube into n naught. N naught is the same thing. And another is that omega, the frequency in hertz. This is in hertz, not the angular frequency. Okay, I am writing omega, but it is in hertz. It's 9 root n naught. This is the plasma frequency, which we say. So it will be helpful in solving the numericals. Okay, the potential, the Debye potential. One must know the thing about the Debye potential, which is phi of r is the Coulombic potential phi naught and e to the power minus r by lambda d. So this is the Coulombic one. This is the extra. Right? And the concept was like this. This is a plasma and you have a test charge. Electrons form a cloud over this test charge. Right? And the maximum length up to which this test charge influence can be felt is the Debye length, and after that it slowly gradually decreases, which is not in the case of Coulombic potential. And another thing about these concepts is having that the peak production thing. So this is the peak production of ionosphere, peak production. I will just draw this graph, which will be helpful. That this is for chi is equal to 0, some chi. Okay. So this is the, for chi is equal to 0 is this, for chi is equal to 30 say. So in this way it is increasing. You see this height, the peak production height. So it increases with chi, the zenith angle, right? And fine. And qm, the peak production, it depends on eta, the number density, I infinity, the top of the atmosphere intensity, cos of chi, the zenith angle. It depends on the exponential of 1. E of 1 is the exponential one, and this is the scale height. So of all this it depends. And hm is h log of sigma h n naught sec chi. So it depends on zenith angle, area of cross section, okay, area, this is scale height, this is charge, number density, and this is the zenith. Okay, it does not depends on I infinity. So this is the thing. And another thing is that the time constant, depending on the recombination rates and all those things, will be helpful. Maybe this is alpha recombination rate, the electron density to the power -1. This is recombination rate. This is what I remember, one question was there in this. So these are some key formulas for the Debye potential. And particle nature of plasma, I will also just note down certain formula which are less now. Something related to the, okay, why particle nature? Suddenly particle nature of plasma is when the concentration of charges are less or ions are less. So concentrations of ions are less, then only we can see this particle nature. And mostly you have cyclotron frequencies. So one is the angular frequency. Let me write it. Angular frequency, that is QB by M. And normal frequency is the frequency is nothing but 1 by 2 pi QB by M, right? The time period will be 2 pi M by QB, just opposite of the frequency, okay? And the radius of gyration, which is very important. This radius of gyration is sometimes called as the Larmor radius. This is RG, which is mv perpendicular upon qb. In terms of kinetic energy, it can be written as 2m into k divided by qb. Fine, this is the particle nature. And anything else is there? Week 12 things and 11 things, you can look into the formulations. I am not writing, there are too many formula which are there, but here I will end. So any other questions based on these things? Okay, so if there are no questions, then I stop it here. I will post this particular thing immediately, as soon as possible I can. This PPT as well as the link of the video recording. So I will stop here. All the best for your exams. What I believe is that MCQ type questions will be coming, and which I have seen in other courses also. And you have that scientific calculator will be already there in the computer, so you don't need to take that in the examination hall, and paper will be provided there to just solve certain rough things, and just go and give the exam. It will be a good thing. Just read those presentations which are there in the NPTEL slides, go through carefully, and go through these numerical questions which in the problem solving session we have solved, and this will be, I think, enough. Just remember those formulas which are there, and I think you all will do good. Okay, fine. I am stopping here. Okay, thank you. All the best.